This video we're going to take a look at reviewing a lot of the concepts that you saw in pre-calculus about graphing, quadratic, polynomial, and rational functions. So this is going to be a real fast review. Hopefully you have notes from pre-calculus that you can go back to and review for them. But this fast review, starting with the quadratic functions. And a quadratic function is simply any function that has x squared as the highest exponent. So f of x equals maybe ax squared plus bx plus c. And we say that its parent graph, or what it looks like if you graph it, is going to be this U-shaped thing here, which we call that shape the parabola. And there's a couple key points on the parabola that you should know. The bottom, also called the vertex, is at the point 0, 0. Then there's another point at 1, 1 and negative 1, 1. And then it kind of U's up from those points. And you should know how to do that much quite nicely. From there, you should be able to figure out how a graph shifts based on the function. Now, you've probably seen f of x plus a, where we add something to the function. So in terms of the quadratic, that's going to be x squared plus a number. And when we add a number to the end, that's going to move the graph up a units. Similarly, if we took f of x, the function, and subtracted a, in the case of our parabola, that would be x squared minus a, that's going to move us down a units. Should also know that if we're inside the parentheses, inside the function, if we add a, that's going to be x squared plus, oops, not x squared plus a, sorry, it's going to be x plus a inside the function, the entire thing squared. And when it's inside the function, the background moves, which gives the illusion that the graph is doing the opposite of what we expect it to do. So in other words, adding a is going to move it to the left a units. And similarly, f of x minus a, subtracting a, in terms of the quadratic, that's going to be x minus a squared, is going to move to the right a units. We can also stretch the graph by putting a in front of the function, a times f of x, so that's ax squared in this case. And this is a vertical stretch of a. So in other words, we multiply the vertical coordinate, the y-coordinate, by a, and that stretches everything up. Now, in pre-calculus, you probably saw a strategy which combined a lot of this stuff. So if we have maybe a times f of bx plus c plus d, or in quadratic form, it would be a times bx plus c squared plus d. What we found is that the new y-coordinate, which we called y prime, is equal to the outside stuff. A times the old y, which represents the function, plus d. The new x prime comes from the inside the function. So if we make x prime inside the function, you have b times that plus c equals the old x. And so we would solve this for x by subtracting c and dividing by b to figure out what the new x prime was going to be. So there's two ways to get at a shift. One way is to identify the left, right, up, down. Another way is to look at, based on the function, how x and y are changing, and then recalculating the key points of 0, 0, 1, 1, and negative 1, 1. Both ways work just fine. So let's see if we can graph these functions. Let's graph the function f of x equals 2 times x minus 3 squared plus 1. We see this minus 3 inside the parentheses. That's what moves us horizontally left and right. It's going to move opposite what we expect. This graph's going to move right 3 units. We also see the plus 1. That's outside the parentheses. It's going to move up 1 unit. And we also see a vertical shift, which I should do in a different color. A vertical stretch, I should say, not shift, of 2. And so using that information that we know the original graph, which I'm going to put in gray here, looks like that, with the vertex at 0, 0, and then we've got the point 1, 1, and negative 1, 1. That's the original graph. My new graph I'm going to put in pink. It's going to move to the right 3 units. And it's going to move up 1 unit. So my vertex moves right 3, up 1. That is my new vertex. Then we're going to curve over 1 and up 1 to get the next units, but we want to also vertically stretch it by 2. So we're going to double the vertical movement. Before, the vertical movement was 1 unit. Now when we go over, the vertical movement is going to be 2 units. And so we end up with this new shifted and moved parabola. Now we could have done it the other way, where we look at how the different points are moving. So we could have said, hey, the x minus 3, that's going to change my x coordinate. So what we do is we say x minus 3, x prime minus 3 equals the old x. Add 3 to both sides, and x prime, the new x, is equal to the old x plus 3. Similarly, we would look at the outside stuff, the 2 times the function plus 1. 2 times the function plus 1 is equal to the new y prime. And so we take those key points of 0, 0, 1, 1, and negative 1, 1, and throw them through these shifts. So with the x's, we add 3 to get 3, 0. Whoops. Let's just do the x's right now. With the x's, we add 3. 1 plus 3 is 4. Negative 1 plus 3 is 2. With the y's, we're going to multiply by 2 and add 1. 2 times 0 plus 1 is 1. 2 times 1 plus 1 is 3. And 1 times 2 plus 1 is 3 also. And so now we know the 3 key points on this graph are 3, 1, 4, 3, and 2, 3. And sure enough, on the graph we just drew, 3, 1 is the vertex. 4, 3 is the other point. And 2, 3 is the other point. So 2 ways to get at graphing this function. Let's graph another one. Let's graph negative 2x squared minus 5x plus 3. Now this one's going to be a little bit different on us because now we're not in the right form. So what we're going to do is we're going to use that complete the square strategy that we saw in pre-calculus. In this complete the square strategy, we're going to group the front terms together and factor out our a terms. So we have negative 2 times x squared. Negative 5 divided by negative 2 is positive 5/2 x plus 3. Then we're going to add something inside the parentheses and subtract that same thing from the end to maintain our balance. The way we get that is we take the 5/2, we multiply by 1/2, and we square our answer. So 5/4 squared is 25 over 16. So we're going to add 25 over 16, and we'll subtract 25 over 16. But remember, we have to multiply that by the out front term of negative 2. So when we do that, we get negative 2 times x squared plus 5/2 x plus 25 over 16 plus, I want to notice the negative times a negative makes a positive, and the 2 over 16 is going to make 8. So I'm going to get this 3 to have a common denominator of 8. And 3 times 8 is 24/8 plus 25/8. Now we can factor that perfect square to x plus 5/4 squared plus 49 over 8. Now we're ready to graph. Inside the parentheses, adding 5/4 means we're going to move to the left 5/4 of a unit. Outside the parentheses, which I should do in a different color, adding 4/9 moves it up 49/8, I should have said, sorry. And then finally we have this negative 2 up front, which means we're going to stretch negative 2. And when we stretch it a negative, that's going to turn it upside down. So let's take a look at what this graph becomes. The old graph always has 0, 0, 1, 1, and negative 1, 1 on it. But we're going to shift that over. Let's see how this shifts. We're going to shift left 5/4 of a unit, which is 1.25. And then we're going to go up 49/8. 49/8 is about a little more than 6. So we're going to go up 1, 2, 3, 4, 5, 6. A little more than 6. So here is my new vertex. So that's the vertex. Now from there we'll go over 1 and stretch negative 2. So now we go down 2, over 1 and down 2 with that stretch. And this becomes my new graph. We could have also done it the other way, where we found the new coordinates by taking x prime plus 5/4 equals x, and y prime equals negative 2y plus 49/8, and it would have given us the correct points for all of that as well. What's nice about all this playing with graphs that we've done is this shifting of graphs works no matter what the graph looks like. So for example, if I've got this funky function that we don't know much about, but let's say there's 1, 1, 2, we'll go negative 1, and we'll go 1, 2, 3. We're going to have a point at negative 1, 1. Let's make it blue. Negative 1, negative 1. We'll have a point at 2, comma 1. And we'll have a point at 3, comma negative 2. And so we've got this function. What we are going to do is we are going to graph f of x minus 2 plus 3. And what we'll see is inside the function, the minus 2 will move the graph right 2 units, and the plus 3 will move it up 3 units. And so we should be able to clearly see what the new graph is going to look like. So this first point over here at -1, -1 is going to go right 2, up 3 to get our new first point. Then we take the graph point at 2, 1 and move it right 2, up 3 to get our new point. And this is just counting over on the graph. Then we take the other point, which is at 3, -2, and move it right 2, up 3, and we get another point. And you see we get the same looking function, just shifted the entire thing right 2 units, and then up 3 units. Right 2 units, up 3 units. Right 2 units, up 3 units. So everything did the same shift to create our new function. Let's try another one. Let's do f of negative 3x plus 9 minus 4. And this time we're going to, because we've got that multiplying by negative 3, let's use the other method. The other method, which says the new y, the y prime, is equal to the entire function y minus 4 on the outside. And the new x, x prime, is inside the function, so negative 3x prime plus 9 is going to equal the old x. So x prime equals, we'll subtract 9 and divide by negative 3 to get the new x values. The points on this graph that we're talking about, we're at -1, -1. There was one at 2, 1, and there was one at 3, -2. So we'll make these transitions to get our new points. First, the x's. We subtract 9 and divide by negative 3. So the x's is the first one. -1 minus 9 is -10. Divide by negative 3 makes it a positive 3. 2 minus 9 is -7. Divided by 3 is positive 7/3. 3 minus 9 is -6. Divided by negative 3 is positive 2. Comma. The y-coordinate we're just subtracting 4 from. So -1 minus 4 is -5. 1 minus 4 is -3. And -2 minus 4 is -6. These are now the new points on our graph. So the first point is at 10/3. That's a little more than 3, -5. The second point is at 7/3. It's a little more than 2, -3. And the third point is at 2, -6. And so we end up with this little squished looking thing. That's how we can shift graphs around. Now, if we start to get more general graphs where we don't know what the parent function looks like, we have to start looking for patterns on the graph. Let's look at the graphs of rational functions. Now graphs of rational functions, I'm sorry, not rational functions, polynomials first. We'll get to rationals in a minute. Graphs of polynomial functions. Now polynomial functions, that's your, you got ax to the 5th plus bx to the 4th plus cx cubed plus something like that. What we're going to do is we're going to look at the degree of the leading term to get an idea of what the shape looks like. So if the leading term, the highest exponent, is odd, we've got x to some odd power, and that guy is positive, it's going to look kind of like x to the first power that comes in from one side and goes out the other. Positive slope. However, the actual graph is going to wiggle in the middle. So it'll come in from the bottom, wiggle around, and go out the top. But you notice that pattern as it comes in from the bottom left, out from the top right. Now, if the x is negative, so it's a negative x to some odd exponent, that's going to flip over. It's going to come down and wiggle around and come out. So it's going to come in the top left and go out the bottom right. So that's the odd case. If the x is even, the exponent is even and positive, it's going to look a lot like our x squared that we saw. The catch is it's just going to wiggle a bit more. It's going to come in, wiggle around, and come out. It's going to come in from the top and go out on the top. Similarly, if it's negative x to some even power, it's going to flip over. So it'll come in from the bottom and wiggle around. Maybe it wiggles a lot. It's going to come in from the bottom and out on the bottom. What we know is that each exponent after 1 adds a wiggle, if you will. Each exponent changes a direction. So if I were to ask you to at least draw a sketch of what the graph y equals negative x cubed plus 4x squared plus 3x minus 8 looks like, this is going to be not to scale, just kind of a sketch, knowing the behavior of the graph, what it is going to kind of look like and possibly do. The leading exponent is odd. It's also negative. So it's going to come in from the top left, come out the bottom right. One nice little helpful piece is the negative 8, the part without an x. That's the y-intercept. So we're not quite sure what it's going to look like, but we do know it comes in, and then when I bend, so that's the first power coming in, bend, that's my second power, bend, that's my third power, and back out again. So notice it comes in, that was the first power, bend, that was the second power, bend, that was the third power. each exponent after 1 added a wiggle. Also notice because it was a negative x cubed, the shape went down as it came in and down as it came out. How about this one? Y equals 7x to the 6th plus 3x to the 5th minus 2x to the 4th plus x cubed minus 4x squared plus x minus 3. So just getting an idea of the general shape of this graph. Looking at the leading coefficient and exponent, it's 7x to the 6th. That's positive, so it's going to come in and go out at the top, even exponent. And in the middle, it's going to wiggle. We do want to hit a y-intercept at -3. So it's going to wiggle. In is the first power, wiggle, there's the second, wiggle, there's the third, wiggle, there's the fourth, wiggle, there's the fifth, wiggle, there's the sixth. Every turn, every wiggle is an exponent. So we came in for first, second, third, fourth, fifth, and sixth power. We also notice it came in and out at the top, consistent with even exponents, and a positive coefficient. So this is kind of what the graph is going to look like. Now, it's not to scale, it's not accurate. The actual graph may, wiggle up here. It may have big wiggles, but that's going to be a very similar shape and design to what we're seeing here. Those are some patterns we see about polynomials. I want to plant for a while on some patterns we know about rational functions. Now, rational functions are functions where their f of x equals what we'll call p of x divided by q of x, where p of x and q of x are polynomials. In other words, we've got a polynomial divided by a polynomial in a rational function. And to give you an idea of what one rational function might look like so that we can talk about it a bit, polynomials might have these vertical lines that we call asymptotes. It might even have a horizontal asymptote. And what these asymptotes are, the vertical asymptotes are places the graph is getting closer and closer to, but never crossing. So you notice these graphs get really close to those vertical asymptotes, but they never cross. Actually, let's do a different color. That's getting too green. So on the inside here, you see this blue graph comes up, then comes back down, and it just gets really, really close to that asymptote. It's going to always get closer, but it'll never get there. The horizontal asymptotes, the flat ones, are things the graph is going to get close to on the edges. Notice the graph can cross a horizontal asymptote in the middle. Horizontal asymptotes only affect what happens on the edges. So on the edge, this graph is getting closer and closer to that horizontal asymptote and never getting there. Vertical asymptotes, the graph will never touch. So you notice the vertical asymptotes, the green lines, the graph gets closer to it, but it never touches it. That's kind of the idea behind Zeno's paradox. Zeno said, I can't make it to work today because before I get to work, I have to get halfway there first. But before I get halfway, I have to get half of that first. And before I get halfway, I have to do half of that first. And you can see if I always have to go halfway first before I get to my destination, I can never get started. So therefore, I can't get there. Good excuse. Won't work on the test day. So that's kind of a rough sketch of what we're talking about. Also, another thing that can happen in a graph is at certain points there could be a hole in the graph. And let me do that in a different color. A hole in the graph. And that is just a spot where the graph looks like it's going to go through, but it doesn't actually go through that point. It's like a gap that the graph has to jump over. And it kind of happens, looks like randomly in the graph, but we'll look at what creates a hole, what creates an asymptote. A couple other interesting things might be helpful to us are these x-intercepts. Is where the graph crosses the x-axis. We also might be interested in the y-intercept, where the graph crosses the y-intercept. So let's give some mathematical meat to this. Let's talk about first how we can find an x-intercept. An x-intercept happens when the function equals 0. Well, if we multiply the fraction by the denominator, it's going to turn out that the denominator times 0 is 0, so we're really interested in when the numerator equals 0. So that's the first important piece. We're finding where the numerator equals 0. That's the x-intercept. The y-intercept is at f of 0. In other words, we're going to plug 0 into the function, and we'll figure out where the y-intercept comes out. Now, for holes and vertical, let's do vertical first. Holes and vertical asymptotes. What we will do is we will factor and reduce the fraction. The part that divides out, the part that reduces, say factor, the factor that divides out makes a hole in the graph. Factors left in the denominator make vertical asymptotes. And the way we calculate those is we make them each equal to 0. So if it reduces out and divides out, that makes a hole in the graph. It kind of disappears. That's the hole. If it's left in the denominator, that creates a vertical asymptote. Now for horizontal asymptotes, what we're going to be interested in doing, we're going to be interested in finding and reducing the leading coefficients. When we reduce the leading coefficient, we might end up with a number divided by a number. That is the horizontal asymptote. However, sometimes we still have some x's left. We might have a number divided by a number times x. Maybe it's x squared, maybe it's x cubed. The idea is that if the x left in the denominator gets bigger and bigger and bigger, we'll have a small number divided by a big number, which is really, really small. Because it's so small, we say the horizontal asymptote is 0, or the x-axis. So maybe I should make the arrow go the other way, because that is not the horizontal asymptote. The horizontal asymptote is actually the x-axis when we reduce the leading coefficients. If we reduce the leading coefficients, though, and x, maybe it's x squared, maybe it's x cubed, whatever it is, if x ends up in the numerator, there is no horizontal asymptote. The horizontal, it's actually a slant or a curved asymptote that's going to approach another function. For this course, we're not going to worry about different shaped asymptotes. All right, enough theory. Let's do it. Let's do some examples. Let's graph 2x squared plus 5x plus 2 over 2x squared plus 3x minus 2. First, we'll find the x-intercepts. Remember, to find an x-intercept, we make the numerator equal to 0. 2x squared plus 5x plus 2 equals 0. And we can solve this one by factoring. It's 2x times x, 2 times 1, and they're both positive. And so we can see really clearly that x is negative 1/2 and x is negative 2. These are the x-intercepts. We can find the y-intercepts by finding what f0 is, plugging 0 into everything. So 2 times 0 squared plus 5 times 0 plus 2 over 2 times 0 squared plus 3 times 0 minus 2. And the nice part about zeros is those all go to 0, so we have 2 over negative 2. The y-intercept is at y equals negative 1. That's the y-intercept. Now that we found the x and y-intercepts, we can start looking for vertical asymptotes and holes. I'm going to abbreviate here. To find vertical asymptotes and holes, we factor our expression. Now the numerator we already factored. It's 2x plus 1 and x plus 2. The denominator we're going to try and factor. So it's 2x times x. We've got a 2 and a 1. And it looks like we want a positive 2 and a negative 1. When we do that, the x plus 2's divide out, which means the x plus 2 equals 0 divided out. So x equals negative 2. There is a hole, because it divided out, a hole at negative 2. The other denominator, 2x minus 1, is going to create our vertical asymptote. So if we solve that one, we got 1/2 is the vertical asymptote. So this graph has a hole, and this graph has a vertical asymptote. The last thing we want to do is find the horizontal asymptote. For the horizontal asymptote, we look at the leading coefficients, the highest exponent part, 2x squared over 2x squared. 2x squared over 2x squared, and reduce that to simply 1 equal to y. That is the horizontal asymptote. So now that we've found all the characteristics of this guy, let's see what his graph looks like. And let's do it on a black grid. Very straight lines. And what we know, first, the x-intercepts are at -1/2 and -2. So -1/2 and -2, those are our x-intercepts. We also found out that our y-intercept was at -1. So the y-intercept, which we did in green, is at -1. We also found out that there's a vertical asymptote at 1/2. So at 1/2, there's a vertical asymptote. The graph's never going to cross that. We also know that there's a horizontal asymptote at 1. Now here's something interesting. We haven't talked about the hole yet. The hole for this graph is at -2. But notice we put a point in at -2. Turns out this time that hole is the same as the x-intercept. So we want to actually get rid of that point. That's actually going to be a hole in the graph. So the graph isn't going to behave there like normal. And so what our graph is actually going to do is come in and bend down there. And normally after it hits -infinity, it's going to pop up to +infinity and bend down there. We just need to make sure we clearly show the hole in the graph at -2. So because that -2 divided out, it became a hole in the graph. It's not actually an x-intercept. It's a hole in the graph, and so it doesn't quite behave like we expected it to. Let's graph one more before we're done for the day. Let's graph x plus 1 over x squared minus x minus 6. And just to make it easier for us to see if we need to do any reducing, we've got x plus 1 over, and then we factor it, x and x, minus 3 and minus plus 2. Minus 3 and plus 2. There's no reducing here, so no funny holes that aren't behaving like we expect them to. So first we found the vertical, or the x-intercepts, which was from when the numerator equals 0. X plus 1 equals 0, so the x-intercept here is at -1. The y-intercepts, that's when we find f of 0, so we have 0 plus 1 over 0 squared minus 0 minus 6. That equals -1/6 for our y-intercept. Because nothing reduced out, there's no holes, but we do have vertical asymptotes. We take x minus 3 equals 0 and x plus 2 equals 0. The vertical asymptotes are at 3 and -2. And for our horizontal asymptotes, we take our leading coefficients of x and x squared and reduce those to 1 over x. Now, because we have x left in the denominator, the horizontal asymptote is at y equals 0, or the x-axis. So let's see if we can piece this information together to make us a graph. First, start with the x-intercept at -1. Now we've got the y-intercept at y equals -1,6, so that's just barely below. Vertical asymptotes are at 3 and -2. So here's -2. Let's do it in the right color. -2 and 3. And the horizontal asymptote is at 0. And notice we went through the point at 0. That's okay because it happened in the middle. Remember, horizontal asymptotes only really care about what happens at the ends, not the middle. This graph does not appear to be giving us a loop. Instead, it appears to be coming down from the edge, going through these 2 points, and then changing directions, continuing to go down. And generally, we see a flip happen in the middle, so we're going to probably see this. So that you see it goes from -infinity to positive infinity at that asymptote. The next asymptote from -infinity to positive infinity. And there is our graph of our function. So a lot of stuff today. It's all review of what we spent about 2 weeks on in pre-calculus. Graphs of functions, quadratic functions, shifting graphs, polynomials, and rational functions. Take a good look at it on the homework. Come to class with questions. We'll see you then.